A little bit by way of review, just to start out, because I defined a bunch of things, and you're going to have to internalize those definitions going forward. The idea of position. X is the position. It's where a thing is located according to a number line. If you're willing to wrap your head around it, it's not that difficult an idea. Somewhere there's a 0, and an object has a location. Like in our example, I think the location was 4. That's a position on the number line that identifies the location of an object or an event relative to that coordinate system. But then the object can change its position, so I defined delta x, the displacement. One of the reasons why we use equations in physics is so that we don't need a lot of words. But in order to keep it clear, you have to know what the symbols stand for. Because to me, this equation that I have first on the slide here reads like a sentence. The displacement delta x, because delta means change, and x means position. This literally reads change in position, is equal to the final position, or maybe you could think of it as the position sometime in the future, minus the initial position, which is the position at the beginning, at the start, before the change in position happens. That change in position is called displacement. Now, some things displace very slowly, and some things displace very rapidly. And as it happens, some things displace in the positive direction, because the displacement can work out positive, and some things displace in the negative direction, because the displacement can work out negative. The rate of change of position on average is called velocity. And here it is, the velocity v on average, because the bar means average. The average velocity is the change in position, the displacement, divided by time. That's a rate. The rate of change of position. We use rates all the time in science. You just take your quantity of interest and divide by the time, and you can think of it as how fast. Because the displacement could be positive or negative, average velocity can be positive or negative, but it's nothing to be worried about, because if I have a positive velocity, it means I'm going in the positive direction. If I have a negative velocity, it means I'm going in the negative direction. Now, I did a bit of algebra to this equation. The second equation here and the third, they don't look remotely like each other, but they are actually exactly the same equation. I just wrote delta x as x minus x naught and did some algebraic jiggery-pokery so that the position at some time in the future is whatever the position is at the start. See, that's x naught, the initial position, plus the average velocity times time. So those are some things that I established. It took me at least a half an hour to come up with that, more, and it took me just a few minutes, now that we know the language, to repeat it. Well, now I'm going to go one step further. It turns out there are many steps that we can take, but for our purposes, I'm going to go one step further and appreciate the fact that the velocity can change. Just like positions can change, velocity can change. So I could write down on a piece of paper somewhere, delta v. And every scientist would read that as the change in position. Delta v as change in velocity, because delta means change and v means velocity. So I'm going to introduce a new quantity that I can use to describe my universe, because that's ultimately my goal, and it's the acceleration, which of course you're familiar with the word acceleration from your everyday lives. Acceleration means going faster in an everyday language sort of sense. Well, in physics, it's a bit more subtle. So I'm going to have to ask you to abandon your everyday ideas about what acceleration is and embrace the definitions in physics. First of all, there's another word that goes along with acceleration in our everyday lives, and that word is deceleration. Whereas to folk out on the street, acceleration means speeding up and deceleration means slowing down. In physics, there's no such word as deceleration. Every change in velocity is acceleration. So if you're speeding up in your car, you are accelerating. If you're slowing down, you are accelerating. It's all acceleration. And it's defined this way. The acceleration, for which I use a lowercase a, is equal to the change in velocity. See that delta v there? You can read that because you know delta means change. The change in velocity divided by the time it takes the velocity to change. Well, the change in velocity for sure is going to be meters per second because those are the units of velocity, meters per second. And time in seconds, so I would write the units as meters per second, which seems a little bit sloppy, but I like writing the units this way because of how I think about acceleration, which I'm going to share in just a second. But we do conventionally get these seconds together and call it seconds squared, so that the units of acceleration are meters per second squared. Position is a vector. It has not just an amount, but also a direction. You're to the left or the right of the origin of your coordinate system. Displacement is a vector, not just an amount, but you either displace in the positive direction or displace in the negative direction. Velocity is a vector because you're either going in the positive direction or going in the negative direction. And so acceleration inherits vectorness. Acceleration is a vector. It has a magnitude, an amount, a certain number of meters per second squared, but it also has a direction. But it's not so easy to explain. It's easy to understand, but it's a little bit tricky because you might assume that positive acceleration means speeding up and negative acceleration means slowing down. That is simply not true. It worries me a little bit even saying that out loud because it sounds very sensible when you say it at first, but it is not the correct interpretation of the sign of the acceleration. Luckily, the correct interpretation is easy. When the acceleration is positive, what that tells you is that you should add meters per second in every second. Let the plus sign of positive acceleration mean add meters per second in every second, which is why I kind of like looking at the units of acceleration this way as meters per second. When I have a certain acceleration, it's telling me to add, or a certain positive acceleration, it's telling me to add meters per second in every second. So let's say I start over here, it doesn't matter where on my number line, and I have an acceleration of positive 2 meters per second squared. It means in every second that passes, I should add 2, and then add 2, and then add 2, and then add 2, and then add 2. And it's pretty obvious that adding velocity successively like that is going to make it go faster and faster and faster. But imagine that I'm already going. So here I am, somewhere on the negative side of my coordinate system. Maybe I'm going this way, and I'm going, 10 meters per second, which is a wild sprint. I can't possibly run at 10 meters per second. So we'll take a little imagination. So I'm running at 10 meters per second, but I have a negative acceleration. A negative acceleration will mean to subtract meters per second in every second. A negative acceleration means subtract meters per second in every second. So if I'm going 10 meters per second, I'm going to go 10, 8, 6, subtracting 2 meters per second in every second, and I'm going to slow down. It's a little bit curious because the way that I just described it, a positive acceleration resulted in me going faster and faster, and a negative acceleration resulted in me going slower and slower, except this. Imagine instead I start over here somewhere on the positive side of my coordinate system, and I point myself in the negative direction. Now, if I have a velocity in the negative direction, if I have a negative acceleration, the negative acceleration prescribes that I subtract velocity in every second. Subtract. But if I have a negative velocity and I subtract, it just becomes more negative and more negative and more negative and more negative. Subtracting velocity away when you already have a negative velocity makes your velocity more negative and you're speeding up in the negative direction. See, so it's not quite so simple, but there are 3 easy ways to keep track of it. Appreciate that positive acceleration means add velocity in every second. Negative acceleration means subtract velocity in every second. And I have this little saying, this is a Shidleyism, same sign speeding. All it means is this. If the velocity and the acceleration have the same sign, then you're speeding up. So if the velocity and the acceleration are both positive, you're speeding up. If the velocity and the acceleration are both negative, then you're slowing down. It's when the velocity and the acceleration have opposite signs that you're slowing down. So it'll be a little bit tricky, and we'll need a little bit of practice to make sure we get right answers. But appreciating these three sort of facts about acceleration is going to make it easy for us to get right answers when we start solving problems. I'm sorry? You're speeding up. Same sign and you're speeding up. When they have the same sign, you're speeding up. So I'm going to take a moment with my new equation, my definition of acceleration. Notice, I'll go faster now just because I don't have any words on the slide because I can read it. The acceleration is equal to the change in velocity divided by the time. I'm going to do the same bit of algebra that I used on my definition of velocity. I'm going to multiply the time to the other side of the equation and write it like this. Delta V is equal to A times T. I simply boosted the time out of the denominator and wrote it next to the acceleration. So the change in velocity is the acceleration times time. But change in velocity, just like any change quantity, is the final value minus the initial value. Final minus initial. So I'll write delta V as the final velocity minus the initial velocity, but then I'll add the initial velocity over to this side of the equation to get where I'm going. The velocity at some time in the future, you know why I like this equation? It predicts the future. I've got an equation that predicts the future of position, and now I've got an equation that predicts the future of velocity. And so I'm very happy. The velocity at some time in the future is equal to whatever the velocity is at the start plus the acceleration multiplied by time. Now, the acceleration multiplied by time is just delta V. So I'm really saying the velocity in the future is equal to whatever the velocity is at the start plus the amount that it changes. By the way, one way you can convince yourself that I'm right about this is by looking at the units of each of these quantities. Velocity, of course, has units of meters per second, and that doesn't surprise me. And the initial velocity as well has units of meters per second. But this creature, acceleration times time, is sort of a new thing, and it might be suspect. But if I look at its units, it's meters per second squared multiplied by seconds, and the seconds in the numerator will cancel the square of the seconds in the denominator and leave me with meters per second. So my equation is what we call in physics dimensionally consistent. Meters per second is equal to meters per second plus meters per second. And now I have an equation for velocity that predicts the future. I've got an equation for position that predicts the future, but I can improve it now that I understand what acceleration is. In a previous discussion, we talked about two graph facts. One of those was that if I make a graph of position as a function of time, its slope is velocity. That's true, but it's not my point at the moment. The second graph fact that I stated was that if I make a graph of velocity as a function of time, then the area under the velocity time graph is displacement. The area under the velocity time graph is displacement. So here I've made a velocity time graph, and I start with an initial velocity here. A velocity at the start, at the beginning, when I choose to start watching the universe do its thing. And I notice just by looking at the graph that the velocity increases in time. You can always, from a velocity time graph, learn about the velocity just by looking at it. But now I want to compute the area under the velocity time graph because I claim that the displacement is equal to that area. Now, it's a little bit tricky because it's not a triangle or a rectangle or anything super simple. It's actually, if I draw this dotted line across here, it's really, I can calculate it as two areas. The area of this rectangle here, which I'm calling area 1, and the area of this triangle, which I'm calling area 2. So my claim is that the displacement is equal to area 1 plus area 2, and I'll compute area 1 first. Well, it's easy to do. How long do I go along the time axis? I go t along the time axis. How far do I go up the velocity axis? V naught. So the area of this rectangle is V naught here on the vertical axis, and time on the horizontal axis. So it's V naught times time. That's what that first area is. V naught times time. I'm going to add to that the second area, and the second area is a triangle. So I'm going to do a 1/2 the base times the height thing, because that's how I find the area of a triangle. So 1/2 the base, that's the reason for my 1/2 here, 1/2 the base of the triangle multiplied by the height of the triangle. Now the base of my triangle is time again. Time along the time axis. So 1/2 the base multiplied by the height. Well, the height represented here on this side of the triangle is a change in velocity. So 1/2 the base times the height, I'm claiming that the height of that triangle is the change in velocity, delta V. But just a moment ago, I suggested that the change in velocity was the acceleration times time. So here in my next step, I write acceleration multiplied by time as the change in velocity. And I might be happy to leave it there, but I've got a t and another t over here. That's weird looking. It's strange to write the equation that way. So I'll bring these two together and call them t squared and get a new equation for the future of position that's better than my old equation. So I'll throw the old equation around and use this one. That displacement is equal to initial velocity times t plus 1/2 the acceleration multiplied by the time squared. So I now have two equations that are going to represent the values in the future. The final velocity is equal to the initial velocity plus the acceleration times time. I can predict the velocity at some time in the future. And now with my new equation, if I appreciate that delta x is x minus x naught, then x is equal to whatever the position is now, plus the average rate at which the position changes based on the initial velocity, plus 1/2 the acceleration multiplied by time squared. Now, a lot of the things that I've said leading up to this were pretty obvious. That equation is not obvious necessarily. I wouldn't imagine that a student walks into physics and says, you know what, I bet that the position of an object is quadratic in time when the acceleration is constant. Nobody says that. This is a consequence of my investigation. As I examine the universe and define these things and stir them around using algebra, I discover new things all the time. So I now have two equations that I can use to predict the future using physics. One last thing. I said that there were 3 graph facts, and I want to give you the last of the 3 graph facts now, and it is actually fairly obvious. I'm going to consider once again the same graph of velocity as a function of time. So here I'll put v on the vertical axis, time on the horizontal axis. I'll start with some initial velocity, and I'll go up like this. That's the same graph, but I'm going to analyze it differently. Just for fun, I'm going to calculate the slope of this graph, just like I did for the position time graph. I calculated the slope of the position time graph and found out that it was meaningful. I'm going to calculate the slope of this graph, which is always the rise of the graph divided by the run of the graph. I learned in math class that's how you do that. Well, this graph runs for a certain amount of time and rises for a certain change in velocity. As I go up the velocity axis, the velocity changes. So the rise over the run on this graph is the change in velocity divided by time, which today I've defined is the acceleration. The acceleration is the change in velocity divided by time and the slope of a velocity time graph. For this example graph that I've put up, you can see that the slope is positive. That would be a positive acceleration. If the slope were steeper, it would be a larger acceleration. If the slope were more shallow, it would be a lower acceleration. If the slope were negative, it would be a negative acceleration. Third graph fact: the slope of the velocity time graph is acceleration.
Mm-hmm.